A chameleon's two eyes can scan different parts of its surroundings using partially independent movements. This gives a stationary hunter an enormous field of view, without requiring it to turn its head and reveal its position. When one eye detects potential prey, the chameleon changes behavior. Both eyes orient towards the target, the head aligns, and the tongue may begin to protrude slightly from the mouth. It is not licking its lips. Once the tongue has been launched, there is very little opportunity to correct its course. The animal must estimate the direction and distance before firing. Chameleons can use changes in the focus of each eye to judge distance, rather than relying entirely on stereoscopic vision in the way humans do. By adjusting its optical system until the insect appears sharp, the chameleon gains information about how far away it is. The strike can then be prepared for that particular range. Inside the mouth, the tongue is arranged around a specialized part of the skeleton. Extending forwards from the hyoid is a long, stiff rod called the entoglossal process. Surrounding this rod is a cylindrical accelerator muscle. Between the muscle and the rod are multiple nested sheaths of connective tissue containing helically arranged collagen fibers. Attached farther back is the extremely long hyoglossus muscle, which will eventually retrieve the tongue. At the front sits the broad, deformable tongue pad that contacts the prey. This entire apparatus must fit inside a relatively small head. It does not rest as one long strip of tissue extending down the chameleon's body. Its components are layered around the entoglossal process, while the retractor muscle is folded into a compact arrangement behind them. Before the visible strike, the accelerator muscle begins to contract. Its fibers squeeze inward around the entoglossal process. Because muscle tissue cannot simply collapse into nothing, this radial contraction also lengthens the cylindrical muscle along the rod. At the same time, the muscle compresses and stretches the collagenous sheaths beneath it. Energy from muscle contraction is gradually transferred into these elastic tissues. This is the critical step. The muscle does not have to generate all the power at the instant the tongue moves. It can contract more slowly, store energy, and then release that energy over a much shorter period. The same principle is used when drawing a bow. The archer's muscles gradually perform work while pulling the string backwards. When released, the stored elastic energy is delivered to the arrow far more rapidly than the muscles could move it directly. The tapered end of the entoglossal process helps control the release. As the loaded accelerator muscle and connective tissue sheaths move towards the tip, they remain wrapped around the stiff rod. Once they begin sliding over its end, inward forces are redirected forwards, and the compressed system recoils. The tongue apparatus is fired off the rod. The accelerator muscle, elastic sheaths, tongue pad, and folded retractor structures all accelerate forwards together. Once clear of the entoglossal process, much of the tongue's journey is ballistic. Its initial launch and momentum carry it towards the prey, rather than a muscle continuously pushing it throughout the entire flight. This is why the strike can exceed the direct power limits of vertebrate muscle. In one 47mm chameleon, researchers recorded a peak acceleration of 2,590 meters per second squared. The calculated peak power demand exceeded 14,000 watts per kilogram of accelerator muscle. These are extreme measurements from a particularly high-performing small species. Not typical values for every chameleon, but they reveal the principle clearly. Elastic recoil is amplifying the power supplied by muscle. The tongue's apparent length is equally remarkable. Across the species studied, maximum projection averaged around 1.5 times the chameleon's snout-to-vent length, but the smallest species sometimes exceeded twice that. One reached approximately 2.5 times its snout-to-vent length. This does not mean that every part of the tongue stretches uniformly like a rubber band. The nested sheaths slide and extend relative to one another, while the long, folded retractor structures deploy behind the projectile. It is closer to a biological telescope being rapidly unfolded than a short tongue simply becoming several times longer. Unsurprisingly, the smallest chameleons produce some of the most extreme relative performances. Their tongue apparatus is proportionately larger than that of many bigger species. A small animal must also reach its launch speed over a shorter distance, requiring greater acceleration. The result is that tiny chameleons can project their tongues farther, relative to their body size, and achieve greater acceleration than many of their larger relatives. After the initial burst of acceleration, the tongue travels towards its target at roughly constant velocity for part of its journey. As it approaches maximum extension, it begins to decelerate. This controlled slowing is important. If the tongue simply reached the end of its range at full speed, it would produce a violent jerk and become difficult to retrieve. The extended retractor structures help limit the motion, while the strike is timed so that the tongue pad reaches the insect before the tongue stops. The chameleon is therefore not merely firing as hard as possible. It must select a launch appropriate for the distance. Too little projection and the tongue falls short. Too much, and it risks poor contact or unnecessary strain on the apparatus. Reaching the prey, however, does not guarantee a meal. A hard projectile could simply hit an insect and knock it away. The chameleon's tongue pad instead deforms around the prey, increasing the contact area. Specialized muscles can draw the center of the pad inward, creating a cup-like grip and a suction component. The tongue surface also carries extremely viscous mucus. Measurements from veiled chameleons found it to be around 400 times more viscous than human saliva. This does not behave exactly like a permanent glue. As the tongue begins pulling away, the mucus resists being drawn into a thinner layer. The larger the contact area and the greater the viscosity, the more strongly this wet connection resists separation. A physical model found that viscous adhesion alone could account for the capture of surprisingly large prey. Chameleons have been observed taking animals weighing up to about 30% of their own body mass. In reality, viscous adhesion works alongside deformation of the tongue pad, suction, and physical contact around the prey's surface. The projectile has now become a retrieval system. Retraction is powered mainly by the long hyoglossus muscles connecting the tongue to the hyoid apparatus. These muscles do not use the same rapid elastic launch mechanism. They contract continuously to pull the tongue, pad, and captured prey back towards the mouth. The retractors are unusually capable of producing force across a wide range of lengths. This matters because they may begin pulling when the tongue is only partly extended, or when it has traveled almost its maximum distance. They must also retrieve prey of different sizes without losing it halfway. As the tongue returns, the hyoid apparatus withdraws, the retractor muscle refolds, and the accelerator complex is drawn back over the interglossal process. The jaws then close around the prey, and the entire system is reset for another strike. The difference between launching and retracting the tongue produces one final, unexpected advantage. Chameleons are ectotherms, so their muscle performance normally declines as their bodies become colder. Directly muscle-powered tongue retraction slows substantially at lower temperatures. Elastic projection is far less affected. In experiments with veiled chameleons, reducing body temperature from 25 to 15 degrees Celsius caused projection performance to decline by less than 20%, while measures of retraction performance fell by more than 42%. The muscle may load the elastic tissues more slowly in the cold, but once sufficient energy has been stored, the recoil remains extremely rapid. For an ambush predator, a slower reset is less important than preserving the speed of the initial attack. The insect must be hit before it escapes. Bringing it back can take slightly longer. What appears to be one simple flick of the tongue is therefore a precisely divided sequence. The eyes find the target and calculate its range. Muscle gradually loads elastic tissue. The tongue releases from a tapered skeletal rod and telescopes outwards. A deformable pad, suction, and viscous mucus secure the prey. Finally, specialized retractor muscles draw the entire system back into the mouth. The chameleon's tongue is not fast because its muscles suddenly contract at impossible speed. It is fast because muscular action charges it before the tongue even starts to move.